All right, Unit 8, Acquisition 3, we are continuing on with pH calculations. Today we're going to calculate the pH of weak acids and weak bases, and then we're also going to calculate Ka and Kb. So first, the difference between a strong acid or base and a weak acid or base is the level to which it dissociates. So in the last video, when we did strong acids, we said strong acids or strong bases completely dissociate. So we assume that the concentration of a strong acid would be equal to the hydrogen ion concentration, and the same thing for our strong base. Well, weak acids only partially dissociate. So that means that their concentration will not be equal to that hydrogen ion concentration or the hydroxide ion concentration. So we're going to go through how to calculate pH when those two values are not the same. The other thing we're going to do today is calculate Ka and Kb. So Ka just tells us the degree of dissociation for an acid. So the weak acid only partially dissociates. If I calculate Ka, that will tell me the degree to which it dissociates. Kb is the same thing for the base. So Kb tells us how much does that base dissociate. Alright, first calculation. Calculate the pH of acetic acid if its concentration is 0.03 molar and its Ka is equal to 1.8 times 10 to the negative 5. Alright. So there's a few things that we have to do. The first thing we're going to do is write out our equilibrium expression. So I have my weak acid, and it's going to dissociate. So it's going to break up into its individual ions. And we know that acids are going to donate a proton. So one of those hydrogens is going to get pulled off. All right, I can also now write my Ka expression. So we're going to write this just like every other equilibrium expression, products over reactants. Alright, so I know Ka, so I can plug in Ka to my equation, and I know the initial concentration of acetic acid, but I don't know the concentration of my conjugate base, and I don't know the concentration of H+. So to figure this out, we can do a Rice table. Alright, so the initial concentration of acetic acid is 0.30. And again, before it dissociates, we're always going to assume that we have no products. Concentration of the reactant is always going to decrease. Concentration of the products are always going to increase. So reactants will always be minus X, products will always be plus X. Alright, so now that I know my concentrations at equilibrium, I can plug these values into my equilibrium expression. I'm also going to plug in my value for Ka. And then to simplify this, since it's x times x, I'm just going to change this to x squared. All right, so to solve this, we would have to use the quadratic formula. But since my Ka is very small, 1.8 times 10 to the negative fifth, that means that equilibrium is going to lie far to the left. Equilibrium is going to favor the reactants. Remember, if K is less than 1, our equation favors the reactants. And since it's so small, it's going to lie very far to the left. So we are going to assume X is negligible. Once we solve for X, we'll go back and I'll show you the rule of thumb of when we could just ignore X in the denominator. All right, so let's just assume that X is negligible. So now I have Ka is equal to x squared all over 0.30. And now I could solve for X. I can multiply both sides by 0.3, and I would get 5.4 times 10 to the negative 6th is equal to x squared. I could take the square root of both sides, and 2.3 times 10 to the negative third is equal to x. All right, let's go back up to our question. We are trying to calculate the pH. Well, my equation for pH is equal to the negative log of H plus. Well, I know that X is equal to 2.3 times 10 to the negative third. And then let's look at our rice table. The concentration of H at equilibrium is equal to X. So that means that this value, 2.3 times 10 to the negative third, it is equal to X, but it's also equal to the concentration of H plus. So pH is equal to the negative log of 2.3 times 10 to the negative third. My pH is probably pretty close to 3. When we plug this in, I would get 2.63 as my pH value. All right. Let's go back and talk about that X in the denominator. So I had 0.30 minus X, and we just kind of ignored that X and just made the denominator 0.30. So we want to check to make sure that that X actually was negligible. And this is going to be our 5% rule. So what we want to do is take X and divide by the initial concentration of that weak acid. And as long as you're less than 5%, we can ignore X. So X was 2.3 times 10 to the negative third, 0.0023. The initial concentration of my weak acid was 0.30. Multiply by 100 to get to percent form. And it's going to be less than 1%. So if you could take X and divide it by that initial concentration of your acid and it's less than 5%, X is going to be negligible. And if you think about it, that should make sense. It's not going to make a difference in your calculations, especially when you think about significant figures. If I took my initial concentration minus X, and then we were to get 0.2977, when we round this to significant figures, I still get 0.30. So that value did not change. So that's why we can assume X is negligible. For this class, X is always going to be negligible. If you're going on to AP Chemistry next year, you will have to solve using the quadratic formula. But again, it's always a good idea to check. Take the initial, take X and divide it by the initial concentration of the weak acid, multiply by 100, your answer should be less than 5%. All right, next problem. Calculate Ka if the pH of 0.10 molar formic acid was found to be 2.38. So if I'm going to solve for Ka, I need to write an equilibrium expression. To write an equilibrium expression, I need to write my reaction. So this is a weak acid. It is going to partially dissociate. Since it's an acid, it is going to donate a proton, so I'm going to pull a hydrogen off. So to solve for Ka, products over reactants, I'm going to need an equilibrium concentration of the hydrogen ions, equilibrium concentration of my conjugate base, and I'm going to divide that by my concentration of formic acid. Excuse me. All right. So I'm also going to need a rice table because I need to solve for equilibrium concentrations of all these species. So I know that the initial concentration of formic acid is 0.10. Always going to assume the initial concentration of my products is 0. Reactants will decrease in concentration, so minus X on that reactant side. Products will increase in concentration, so plus X on my product side. All right, so once we have the rice table filled out, the next step is we want to solve for X. Well, X is going to be equal to the hydrogen ion concentration. If I have the pH, I could solve for the concentration of H+. So the concentration of H+ is equal to 10 to the negative pH. So I can take 10 to the negative 2.38. My hydrogen ion concentration is 4.2 times 10 to the negative third. And again, looking at my rice table, the concentration of those hydrogen ions at equilibrium is going to be equal to X. So I know that X is 0.0042. So now I can solve for the equilibrium concentration of formic acid by taking 0.10 minus X and I can solve for the concentration of the conjugate base. Well, that's just going to be equal to X, so 0.0042. All right, now that I have all of my concentrations, I can now plug them into my Ka expression. So concentration of H+ 0.0042. Concentration of my conjugate base, 0.0042. Concentration at equilibrium of formic acid, 0.0958. And then we can solve for Ka, 1.8 times 10 to the negative fourth. Remember, the smaller the Ka value, the weaker the acid. So since I have a Ka value less than 1, I know this is going to be a weak acid. It only partially dissociates.